Uh, okay, so let us begin the second day, and we'll have the second lecture by Sandra Schottky. So thank you all for coming back. I'm glad you're back. This means I haven't scared you completely yet. So my plan is not to talk about any of my own work, in case you haven't figured this out yet. I'm also still not an expert in integrable systems, and I'm unlikely to become one by the end of the week. So any comments, corrections you may have, please share them. The plan for today is to do Jacobians of Riemann surfaces, and I'm not solving any differential equations, and the derivative will never appear on the blackboard today. And I know that at the beginning of yesterday I said motivation was to speak less loudly. Okay. I said the motivation was to try to solve some differential equations, and I have shown you some differential equations. We haven't solved any of them. We will do so next time. So today is going to be mostly about Jacobians. Raise your hand if you have ever had a class in algebraic geometry in your life. Okay, good. Well, if you taught a course without having one, raise your hand. Good. Okay, so I wanted to talk about Jacobians. And I wanted to talk about abelian varieties. And I did this last time, but let's try to review this quickly. So an abelian, a complex torus, is abstractly a quotient of c to the g by a lattice, whereby the word lattice, I mean it's a group, an abelian group in c to the g isomorphic to z to g. So it has two g generators, and it has to be full rank, which is to say that if I tensor it with R, I get all of c to the g, which is just to say that as vectors in R2G, the 2G generators are linearly independent. That's what a complex torus is. Okay? You can always choose a basis, can always make, G generators of the lattice be a basis, a complex basis of c to the g, and then write the lattice as z to the g, because this is a sublattice generated by the first g generators, plus whatever the other g generators generate, and they generated a copy of z to the g times some tau, right? Where this tau is a g by g complex matrix. Okay? So you can think that every complex torus has a quotient c to the g by such a lattice. Okay, we have specifically chosen this to be the case. If you have a good taste in mathematics, you know that when I say the word complex torus, you should be unhappy. One should define some category, right? And one should talk about morphisms and so on. I'm not going to do that, but we should think about morphisms of complex torus. So what do I mean when I say a morphism? This means in the category I operate in, which means complex. So this means I need to have holomorphic maps of complex tori, right? If I have one object of this form and another object of this form, and I have a holomorphic map from one to the other, I can lift it to the universal covers. I'll get a map of CG to CN. I'm most interested in maps CG to CG. A lift of a map of complex tori will be a map of CG to CG, which has linear growth. And there's going to be a holomorphic map of CG to CG, which has linear growth, which must be a linear map. Okay? So all of this leads me to an exercise, and I should keep my tradition of having some color for exercises. For g equal to 1, which is the classical case of elliptic curves, when two complex tori, which of course you're going to think of as C quotient Z plus Z tau 1 and C Z plus Z tau 2, biholomorphic. Okay, and then you should also ask which complex tori of dimension 1 have automorphisms, endomorphisms. Understanding what these words mean is part of the exercise. I want to say this, and then it's up to you to interpret the problem. Okay? So the correct question would be not which complex tori have automorphisms or endomorphisms, but describe the group of automorphisms or endomorphisms of each complex torus, which would address Pasha's control. I'll continue. Okay? Yes, so this form rings. So that's what it means to be a complex torus. An abelian variety is a complex torus T which can be embedded in a projective space. This is CPM, right? So an abelian variety is just a complex torus that admits an embedding into a projective space. And there is a theorem, which is Riemann's bilinear relations, which says that a quotient, as described above, in this form, is an abelian variety if and only if tau is symmetric and the imaginary part of tau is positive definite. Nice exercise, but maybe exceeds the real scope of an exercise. Okay? So I'd be interested in abelian varieties, and let me now tell you why I'm interested in this. Well, you'll see this shortly. So if I have X is any algebraic complex variety, polarization on X is the C1 of an L, where L is an ample line bundle. On X. I don't want to define what this is. This is not where we're going. But I want to say that if X is smooth, a polarization is just a class, C1 of L, which is a Schurn class of a complex line bundle. So it's going to sit in H11 of X with complex coefficients, which is positive. That's what I write, positive. It makes sense to talk about positive classes. They give me a pairing, and I want it to be positive. But it's also a C1, so it better be an integral class. Okay? So that's what it means to have a polarization. A polarization is a class of a positive, ample, however you want to think about it, line bundle. That's what it is. I don't want to say what ample is. You can ask what this means for an abelian variety, and this is easy to see. A homology of an abelian variety, the homology of a complex torus is very easy to compute, right? It's just generated by H1. Okay? A polarization is called principal. L, C1 of L is called principal if the dimension of the space of sections is precisely 1. Okay? Does this clarify a little bit what we did last time? Or repeat it? Am I too loud, or am I the only one here in an echo? Okay, I'm good. Okay, so I now want to tell you an ad hoc, I guess the physicists would like to say the word ansatz. I'm not going to say the word ansatz, for why this is true. So I want to tell you, given any tau, which is like this, right? So it's a G by G complex matrix, which is symmetric with positive definite imaginary part. I want to tell you how to define a principal polarization on this quotient. So definition. For any tau in the Siegel space, so this is the Siegel space. This is what I wrote last time also. So these are G by G complex matrices satisfying the condition that they're symmetric and positive definite. And for any Z, which is an element of C to the G, the theta function, theta of tau and Z, whether you call this tau or tau depends on which side of the Atlantic you're going to be. I'll keep saying tau probably. And this is either Z or Z, depending on which version of English you speak. So this is theta of tau and Z. I'm American. Okay. This is the sum over all integers n and of the exponential of pi I n transpose tau n plus 2z. Okay. Something. I wrote a formula. We should convince ourselves that at least we know how to read such a formula. This is a g-dimensional vector. This is a g-dimensional vector. I can take scalar product. This is a g-dimensional vector. This is a matrix. This is a vector. So at least what I wrote makes sense. The fact that the tau is symmetric makes this nice. The fact that the imaginary part is positive definite makes this convergent. Because morally things, this is like I, right? The imaginary part is positive definite. So this is like exponential of minus n squared. This is what makes it convergent. Of course, the actual proof is a bit more complicated, but morally, that's what the proof is. So, exercise. This is an easy one, but this is just to familiarize yourself with the formula. It says the following, that for any m1, m2 integers, theta of tau z plus m1 plus m2 tau is equal to theta of tau z times some non-zero factor depending on m1 and then m2. Which part of the exercise is to write this factor explicitly. Okay? This is reasonably easy to check. You basically just need to rearrange the summation so that it goes differently. Okay? I'm not going to go into this. This is an easy exercise. Why am I telling you that? Because this means that this exercise has a corollary of... Pasha, don't spoil the exercise, please. The dependence is allowed to be trivial. I never said anything else. Yeah, so of course Pasha is correct. So the theta function is just periodic with respect to m1. So this does not depend on m1. Also, I have hopefully by now, yes, I have made the traditional mistake in the field. So this is tau times an integer. Here I wrote integer times tau. I should be doing the same thing always, and I was very carefully sloppy. So whether you multiply on the left or right should be done consistently. I have not bothered. When you're doing the exercise, you'll figure out the right way to multiply. Okay? Otherwise, it won't work. So the corollary of the exercise is the following. I can define a locus theta tau inside a sub tau. So this is the quotient, right? C to the g, z to the g plus tau z to the g. Hopefully by now, no, I haven't yet messed up. So this is a locus defined by the following. Theta tau is the locus of z in a tau such that theta function vanishes, is well defined. What do I mean by this? Of course, I've written a function. If you trust me, this is a well-defined holomorphic function on C to the G. Of course, its zero locus on C to the G is well-defined. But I claim that its zero locus descends to the abelian variety, right? Which is to say that the zero locus is independent under translations by this lattice, right? But that's exactly what this what this exercise says, right? It says that if I add an element in this lattice to Z, whether this is 0 is the same as whether this is 0, right? The 0 locus is independent. It doesn't mean that the function is the same. It just means that I've multiplied by a constant. Constant means this non-zero factor does not depend on Z in particular. Okay? So this is called the theta divisor. Fact. Fact means I don't want to prove it. I don't want you to prove it, but I want you to believe it because we have to. Theta tau defines a principal polarization on A sub tau. Okay? Let's parse what this says. So the theta tau is a subset of A sub tau. It's a codimension 1 subset of A sub tau. So it's a divisor on A sub tau, right? It has a homology class, which is a class in H11 because it's a complex subvariety of codimension 1. It's a well-defined subvariety, so it's an integral class. I'm claiming that it's an ample class, which I'm not proving. I'm moreover claiming that the dimension of the space of sections is 1. This is a bit sloppy. So from now on, when I say polarization, I will pretend that I can think simultaneously of 3 things. An ample line bundle, its Chern class, and the section. Okay? And I will write theta for all of the above just to confuse you. Okay? Beware that this is sloppy because I can take the theta and I can translate it. Remark, for any point V, let's say, in the abelian variety A sub tau, I can translate theta by V, which is to say, consider the 0 locus of Z such that theta tau Z plus V is 0. Okay? If you're thinking of this as a subvariety of C to the G, this means you just translated it by, well, either V or minus V, depending on how you think about things, okay? This will be my convention. I want to write it on the blackboard. And the Chern class of this is not going to change, right? So this, for me, will be denoted translation by V of the theta divisor. Its Chern class is the same class, but of course it's a different function. Yes, Pasha?
Yeah, maybe it makes sense to mention that this theta should tau is a great variety. You could maybe refer to Cho's theorem. Or actually, so the theorem I stated last time, which is data. Analytic line bundle defined by theta.
I could say all of this, but I won't. I want to go another direction. Yes, there is quite a bit of stuff hidden here, of course, right? You need to check something. There are some choices involved. I wrote some formula, right, which is really a formula dependent on a point in the Siegel space. The isomorphism classes of abelian varieties are not the Siegel space, but a quotient by the complexity group, which I'm not going to write again. And I'm also claiming that this choice is reasonably well defined under the action of the complexity group. There are many things that I'm hiding, but this is not the direction I want to go to. Okay? Any questions so far? So, I mean, I wrote an explicit formula for an explicit function, and I made some claims about that function. Are the claims okay? Yes? Okay. This is what I wanted to say about abelian varieties. Mostly, one last thing is, of course, that AG is the moduli stack. Yeah, maybe I should write this quotient. Moduli stack, moduli space of principally polarized abelian varieties. And as I said last time, it's a quotient of the Siegel space by the complexity group, by the integral complexity group. And I don't want to discuss this as an exercise today in the exercise sessions, but I'm happy to discuss this privately. So this is basically clear from the description we have done so far. And in particular, what you can observe from here is that the dimension of the moduli space for abelian varieties, I claim that it's a complex stack, manifold. So it has a well-defined notion of dimension. which is the same as the dimension of this gadget, right? Because I'm taking a quotient by something discrete. The dimension does not change. What's the dimension of this gadget? This is symmetric G by G matrices, okay, we know the dimension of that, with positive definite imaginary part. Well, that's not open condition, so it doesn't change the dimension. So the dimension is G times G plus 1 over 2, by which I mean, of course, the complex dimension. And that's the dimension of the space of complex G by G matrices, which are symmetric. Okay? Now, the next plan is to go to Jacobians. Okay? All good? Questions, complaints, corrections? Yes? Because I'm more used to writing it this way, but I have already made many mistakes about left or right. So if I write this on the left here, this should mean I should write tau on the left or right correctly. The Siegel upper half space is really a locally symmetric space. It's a quotient of SP2G. I mean, I will admit, but not in public, that the Siegel upper half space is really SP2GR quotient by UGC. And if I write this quotient on the right, I better write the other quotient on the left. I have to make, once and for all, I have to make consistent choices. But there is only one choice to make. So if I write it this way, then whether the lattice is tau times z to the g or zg times tau, I should also know which one is correct, except I'm not bothering with this. Okay? If you look at the papers in the literature, half of the papers make this mistake somewhere. So it's fine. Okay? So Jacobians of curves. So I wanted to tell you or remind you about what divisors are. So my curve continues to be denoted C, with apologies to Pasha, who I think denotes curves by X. But I'll have to stick to that. Okay, but that's not the same curve C. So I'll have curve C. And I want to say that, I want to remind you, so that a divisor on C is just a sum of mi pi, where mi are integers and pi is a point on C. It's just a formal linear combination, finite sum. Okay? The divisors on C form a group. There is a degree map from divisors to integers. Which just takes the sum of all the coefficients. Okay? If I have a function f on C, so it's a function which means a meromorphic function, so it's a map from C to P1, then the divisor of f is the following. It's a sum of zeros of f, zero z of f, times the multiplicity of f at the 0 minus the sum of multiplicities of the poles. Okay? Which I can also write as just the sum of all points P and C of the order of f at P times P. Okay? So the divisor of a function is the sum of its zeros with multiplicity minus the sum of the poles with multiplicities. This is manifestly a finite sum, right? Because there are finitely many zeros, finitely many poles. I write it schematically this way. You should complain. This is a sum of all points of C. This is certainly not a finite sum, right? But the coefficient is the order of f. The order of f is 0. It's a regular point for a generic point of P. So this is the same, it's just a shorthand for this, if you wish. Okay? That's what a divisor is. Then Picard group of C is the group, divisors are denoted divisors, quotient by divisors of functions, called principal divisors. So the divisors divisors on C are an abelian group, right? I can add two such expressions just formally together. And then there is a subgroup of this group, which is obtained by taking divisors of functions. So I better convince you that this is a subgroup. Well, this is easy because I can just tell you the divisor of f times g is equal to the divisor of f plus the divisor of g. Okay? So this is a subgroup, and the Picard group is the quotient. This admits a map called the degree to z. I told you what this map is here. I claim that the divisor of a function always has degree 0, otherwise this map would not exist, which you know under the guise of the statement that the number of zeros of a function is the same as the number of poles of a function counted with multiplicity. So the degree is 0. Okay?
Maybe it's worth saying that function f would not be zero. And you said it's a method.
I said it's. Okay. I'm happy to have a constant map, by the way. That's not a problem. The divisor just is not there. Okay? If I'm writing this way, I should also write that f is not identically equal to infinity. But yeah. There were so many things I was hoping to happily skip and sweep under the rug. And now I'm not allowed. So Pasha, I'll tell you when you're supposed to not notice. Okay. How many of you have seen the definition of the divisor group and the Picard group? Okay, good. So you can define peak D inside peak. These are the divisors or degree D divisors. And there is, of course, a fact that Picard, D of C, is the line bundles on C of degree D up to linear equivalence. Okay, which Pasha, of course, alluded to yesterday, and I'm not going to prove. Okay, so definition. This is a not very nice definition. I want to tell you what the Jacobian of C is. I told you last time, I took integrals of a basis of homology and so on, but I can just tell you that this is peak, say, G minus 1 of C. Okay? This is just a definition. Notice that this is isomorphic to peak D of C for any D, but this is not canonically. It's just this isomorphism is given by some D in peak G minus 1 minus D. So if I take an element D in peak G minus 1 minus D, I can just add it to any divisor here, and I'll get an element here, right? So if I take any line bundle, any divisor, I'm being sloppy with language because I want to be sloppy with language, of this degree, and if I add it to any divisor of this degree, I'll get a divisor of degree, the sum of degrees, so it's here, right? But this isomorphism depends on this choice of D, okay? I want to think of it this way, because if I think of it this way, I can tell you what the polarization is. This will be principal polarization. On peak G minus 1 of C. So theta is defined to be the locus of effective divisors. Effective means linear combinations with only positive coefficients. So I'll write this as not a sum, I'll write this as P1 plus dot 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 plus Pg minus 1 inside peak G minus 1 of C. So let me try to explain something. So what I wrote here is a linear combination of arbitrary G minus 1 points in the curve, right? This is manifestly a divisor of degree G minus 1. Of course, in peak, I'm not thinking about this. I'm thinking of its equivalence class up to principal divisors. But what I wrote is something, well, there is something to check, but what I wrote, this looks like it should be of dimension G minus 1 unless they're somehow linearly equivalent to each other easily. I never told you, of course, but the dimension of the Jacobian of any peak is equal to G, right? So I have defined for you a locus of dimension G minus 1 inside the locus of dimension G. So it's a divisor, it's a codimension 1 complex subvariety. The claim is that this is an effective divisor. Well, that's clear, I defined the locus, so it's an actual subvariety. The claim is that it's ample and has one section. This I'm not going to prove, but that's the definition of the Jacobian. This is not a definition of a Jacobian that is truly the best, because if I define it this way, it's not clear that Jacobian is a group. And that's not nice. So I'll make one apologetic remark about that, and then I'll forget it. Remark, there exists a natural map, natural, canonical, I don't know what to say, peak node of C times peak node of C to peak node of C, which is just the sum of two divisors, right? So I take a divisor D1 here, and I take a divisor D2 here, and I send it to the sum of two divisors, right? There does not exist a natural map, natural, canonical, whatever, peak G minus 1 of C times peak G minus 1 of C to peak G minus 1 of C, right? Because if I have a divisor of degree G minus 1 and another one of degree G minus 1 and I take their sum, I'm going to get a divisor of degree 2G minus 2, which of course I can then identify with divisors of degree G minus 1, but there is a choice involved. However, I can do the following. So if I take a divisor D1 here and I take a divisor D2 here, I can consider D1 plus D2. That's a divisor of degree 2G minus 2. And I can subtract from this the canonical divisor of the curve. The canonical divisor is the divisor of any holomorphic differential in the curve. So this has degree 2G minus 2. So this gadget lies in peak node of C. Okay? Moreover, peak G minus 1 has a natural involution. Just take D to the canonical minus D. This is responsible for the pseudo-duality, essentially. Okay? I'm not saying anything further. But this is just to warn you that I would like to think of the Jacobian as peak G minus 1, because then I can see the theta divisor, the polarization inside it very naturally. But I'm losing the natural group structure, so there is some choice involved. The choice is really not so big because somehow I need to identify peak node and peak G minus 1. If I wanted to identify peak node and peak 2G minus 2, I would have a canonical identification, which is what I used here, the canonical class. So I should really use a square root of the canonical class, which is known in classical literature as Riemann's constant. But I'm not going to go that way. I'm going to pretend that this issue does not exist. To peak node, okay? Because this was a degree G minus 1, another degree G minus 1, total 2G minus 2. So I always have a map from peak A times peak B to peak A plus B. But then I have the class, canonical class, which has degree 2G minus 2. So it ends up in peak node. Okay? Any questions so far? Yes. How do I see that the theta divisor is dimension g minus 1? Because each of the points pi here, right, is a point on the curve. The curve has dimension 1. So I've written a g minus 1 dimensional set of sums. Of course, I'm then taking a quotient. So you might. Hmm? But I don't know how to sum points. I mean, this is a sum. This is divisor, right? So I don't know. I mean, I don't know how to add points on the curve except to think of the sum as a formal sum, which is a divisor, right? A divisor is a linear combination of points with some weights. So I've chosen all my weights to be 1. And I've chosen to have g minus 1 points. This does not prove that the theta divisor has dimension g minus 1. Because I'm mapping, I mean, as a set of divisors, yes. But then I'm taking the equivalence by principal divisors, by divisors of functions. So this could in principle cut down the dimension. I'm claiming this doesn't happen, but this requires some thought. More questions? Okay, raise your hand if you were aware of all this so far, somehow, more or less. Okay. So this number will now go down a bit, probably. Theorem, Riemann, theta, singularity theorem. So before I state this, let's recoup where we are. So in the beginning, I spent some time talking about modular of abelian varieties, right? And I somehow pursued it analytically. I wrote tau, I wrote the theta function, I wrote the theta divisor inside the given abelian variety. There was a formula. You have an exercise to prove that this actually makes sense, right? Then I had a more algebraic today, the more analytic was yesterday, construction of Jacobians of Riemann surfaces. This is a theorem that describes geometrically better than that what the theta divisor of a Riemann surface looks like. There is no analog of this for a general abelian variety. There are many, many questions about theta divisors of general or somewhat general abelian varieties that are not approachable because there is no analog of this statement. So this is very, very special to Jacobians. The statement I'll write very quickly, and then we'll spend some time parsing it. It says the following. It says for any, I'll write L because I'm thinking of this as a line bundle. So for any degree g minus 1 line bundle on the curve C, which remember is a Jacobian, if I take the multiplicity of the theta function, or the theta divisor, at the point L, right? So the theta divisor is a divisor in here. It's also given by a function. It makes perfect sense to compute its multiplicity, except I should write. It makes perfect sense to compute the multiplicity of a divisor theta in the Jacobian at a point corresponding to L. This is a bit confusing because this is a line bundle on a curve, but this line bundle is a point in the Jacobian. At this point of Jacobian, I can take the multiplicity of this. And the answer is that this is just the dimension of the space of sections. Okay? This is a grand generalization of that statement, right? Because what does it mean that the multiplicity is greater than 0? It means I have a section. If I have a section, it means I can write the line bundle as that. What is a section of a line bundle? A section of a line bundle is, of course, a section of a line bundle. But I can also think of sections of line bundles as meromorphic functions, which I'll remind you of in a second. This is much, much stronger than that. And this sort of describes, quote unquote, completely the theta divisor of a Jacobian. Quote unquote completely because it only captures the multiplicity. There are many more invariants you may want to know. This is much more elaborate. Okay? So what I'm referring to when I was saying something about functions is recall that if L is a line bundle on C, which corresponds to a divisor D in some group of divisors of degree C, then H naught of L is a set of meromorphic functions on C, meromorphic functions f on C, such that the divisor of f plus d is positive, non-negative, which is to say that the multiplicity of every point is non-zero. Hopefully I didn't mess up any signs. Okay, so I'm just saying that how do you think of line bundles? Well, you think that's a line bundle, transition functions, that's all very good. This is all correct, of course. For curves, for Riemann surfaces, a divisor is the same as a point, right? It's a codimensional one thing on a one-dimensional complex curve, so it's a point. So a point is the same as a divisor, the same as a line bundle, right? And then I'm just thinking of, I can trivialize a line bundle outside of a finite collection of points, as Pasha described yesterday. And that's how you can perceive then the sections, okay? I don't want to go too far this direction because that's not the direction we're going. If you have never seen the Riemann-Roch theorem, I have never thought about its proof in this classical spirit, I do highly encourage you to think about it. This is not an exercise that you can really do, but please do think about it if you get a chance. Okay, let's see. Any questions? Exercise. First, for g equal to 1, okay, you have a curve C. Please establish that it's canonically isomorphic to its Jacobian C. What does Riemann theta singularity say in this case? For g equal to, how is C related to the Jacobian? And what does the Riemann theta singularity theorem say then? There is a nice uniform answer to this question in genus 1 and genus 2. All curves of genus 2 sort of look the same. All curves of genus 1 look the same from this point of view.
So the way you define Jacobian, so for g equal 1, it has a 0. Because you said it's big g minus 1. But the curve of genus 1 doesn't have a 0. So this is not canonical.
Did I write canonical?
You said.
Oh, is it true that M1 moduli of curves of genus 1 is equal to A1? Okay? I don't want to comment on that, and Pasha will not comment on this now. So this is this question admits both answers, yes and no, depending on how you think about it. Both are correct. Okay? Okay? This is not something we're going to discuss, but if you really want to check that you really can follow the machinery, figure out what happens for genus 3. So you will discover here from this point of view that not all genus 3 curves are created equal, and you should be able to see how they're not created equal. Tell me what this means. And what can you say about the singularities, right? Is the theta divisor of a Jacobian of a genus 3 curve singular? If it is, what are its singular points? What do the singular points look like? Okay. I mean, I'm aware that look like is not a mathematical term, but this is what I would like for you to think about. Okay. Any questions? Okay, so I want to proceed more in this direction, but let's do an interlude. Yes. A divisor, a Cartier divisor, or any divisor on a smooth manifold, you didn't hear that, is given by a function. And you just see with what multiplicity this function vanishes at the point. So if the function will vanish, its first order derivatives will vanish, its second order derivatives will vanish. That's all. Huh? Wait. I'm very glad that I can. So let's parse this statement again. What is L? L is a line bundle on a curve. As such, it's a point. So this guy here is a point on the Jacobian, right? Yes, I'm aware that it's represented by a line bundle, but the Jacobian of a curve is the moduli space of line bundles on this curve. So as such, L, which is secretly a line bundle on the curve, represents a point in the Jacobian. The Jacobian is peak G minus 1. Theta is a divisor on the Jacobian, right? Or you can think it's the zero locus of a theta function on the Jacobian. So this is a divisor. Theta is a divisor here. So I can ask what is the multiplicity of a divisor on the Jacobian at a point in the Jacobian. And it turns out to be equal to the dimension of the space of sections of the actual line bundle L on the curve. So it relates two very different things. It relates the geometry of the Jacobian here to the geometry of the curve here. Okay? Make sense? And this is indeed extremely confusing because I'm taking multiplicity of a divisor on the Jacobian at the point of a Jacobian that corresponds to a divisor on the curve. And that's what this says, right? And there is no way around it. This is what this statement is. Okay? Let me do an interlude on the Schottky problem, and then we'll return here. Maybe by that time some more questions will arise. Interlude. It's not really interlude. It just doesn't follow in the logically from what I was saying. Schottky problem, which I have alluded to in the beginning. So moduli of curves is denoted mg. Moduli of abelian varieties is denoted ag. There is a map that sends a curve to its Jacobian, right? Theorem, this is called J, for Jacobians. This is Tarelli's theorem, which is to say J is injective. And I'll write here something you cannot read. So this says on coarse spaces, but I meant it to be invisible, and I succeeded. So this is an injective map. So what does it say in words? It says that if I tell you an abelian variety and I promise to you it's a Jacobian, you know it's a Jacobian of what curve, right? This can be quickly proven from here if you follow the machinery. We're not doing this. There are many, many proofs of the Tarelli theorem. That's one of the cornerstones of the moduli theory, many classification problems. This is the first instance of Tarelli theorems from Hodge theory because the Jacobian is a classifying space for weight 1 Hodge structures. And this captures the geometry of the curve. But this goes far beyond what we're discussing. What's the dimension of the moduli space of curves? The dimension of mg is 3g minus 3. This is a very nice thing to check except you won't be able to prove it unless you know that it's really a manifold or an orbifold. But this is, the computation is essentially due to Riemann, modulo many things that needed to be fixed afterwards. The dimension of this space is that, right? You can check what they are, and they're both irreducible. And in fact, the Jacobian map from M2 to A2 or from M3 to A3, they are dominant maps. Dominant doesn't mean they're isomorphisms, it means the image is dense, right? So this means basically every abelian variety of dimension 2 except some smaller, some codimension subset is a Jacobian of a curve. Any genus 3, any three-dimensional abelian variety, principal or polarized abelian variety is a Jacobian of a curve up to smaller dimension subsets. You can check 3 times 4 over 2 is 6, which is the same as 3 times 3 minus 3, right? So you know that this is going to fail. So theorem, this is due to Schottky and goes back to happily 1880s. The proof, of course, was incomplete. So the proof was completed by Gusa in 1970. It says the following. I can write for you the solution of the Schottky problem. I'll write what the statement is, and I'll say this is a solution of the Schottky problem. The question is to know which 4-dimensional abelian varieties are Jacobians of curves. It's
Maybe for the first identity, you need minus 3, you should say that G.
well, this is why I started with M2 here. But since we don't really know whether M1 is A1, that was an exercise, right? So the statement is the following. So I want to know for a given abelian variety, which I'll write as A sub tau, right? Remember A sub tau, which is a 4-dimensional abelian variety, okay, is a Jacobian of some curve, so lies, so this is to say A sub tau lies in the image of M4, if and only if the following condition holds. So the sum theta epsilon delta to the 16th power of tau, 16, 2 to the 4th, is equal to the sum theta to the 8th power epsilon delta tau. Let me put a 0 here. Squared. I'm not done. I have to explain to you what I wrote. Where theta epsilon delta tau 0 for epsilon and delta in z mod 2z to the 4th is essentially, I mean, there is some constant, which I don't want to tell you, depending on epsilon delta, but it's just the value of the theta function as the corresponding 2 torsion point. Okay? So these are the so-called theta constants. And basically what they are, they're just the values of the theta function at various 2 torsion points. So 2 torsion means if I multiply by 2, I get the lattice vector. So it's a point on the abelian variety A sub tau, such that 2 times that point is the origin. Okay? There is some constant factor which is easy to write. I just don't want to bother because we'll never write theta constants again. And so I don't want to waste time in that direction. Notice that this is an amazing result, I think, because this is something that relates 2 kinds of geometry. So this solves the Schottky problem. This describes the image of the moduli of curves of genus 4 within the moduli space of abelian varieties of dimension 4, very, very explicitly. If you have a computer, you can check this in no time whatsoever, right? This is a very nice algebraic equation that fits here, right? I could write it on the blackboard in half a line. I can remember it. I don't have to look at my notes to find out what it is. It's completely explicit. It's one equation because you would expect that this is one equation. Because if you think about the dimension of A4 is 10, the dimension of M4 is 9, so it's codimension 1, so it has to be given by one equation. It's a divisor. Okay, that is the equation. Okay, and I have written it explicitly purely in terms of the theta function. Okay, this is a solution of the Schottky problem. So the Schottky problem is the following problem, which is really the goal of this lecture is to present you a solution to the Schottky problem due to Igor Krichever by flexes of the Kuma variety. We're getting there. Is to describe the locus of Jacobians of curves within the modular space for abelian varieties. And this solves the Schottky problem completely. For g equal to 4. Okay? Yes? There is. I wrote a theta function explicitly for abelian varieties. The formula I wrote was for abelian varieties. Theta of tau z is a sum of exponentials. That was for any tau in the Ziegel upper half space. That knew nothing about the curve. The Riemann theta singularity theorem is something very interesting about curves and so on and so forth. But my formula for the theta function was theta of tau z is some sum of exponentials. That just uses tau, which is a matrix in the Ziegel upper half space, a symmetric matrix with positive definite imaginary parts. And that's all I need to define this function. I never said that. There is a theta function for abelian varieties. There is no theta singularity theorem of any kind. I have no idea how to do that. But the theta function is well defined. The theta function is the polarization, right? So the principally polarized abelian variety has a principal polarization, commonly denoted by theta, written explicitly analytically in the formula I wrote down. It's there. For a Jacobian of a curve, the theta function has this beautiful geometric structure, which is lacking for a general abelian variety. But this is well defined for any point in the Ziegel space, really. That's what I wrote, right? Of course, this is a Ziegel modular form, which are words I'm not going to say. So this is well defined not on the Ziegel upper half space, but on the modular of abelian varieties, but never mind. More questions? Yes? On a Jacobian of a curve, yes. Correct. So I defined theta function in two different ways. I defined the theta function by a formula sum of exponentials for any principal, for any abelian variety. For any tau in the Ziegel upper half space, which is the universal cover of the modular space for abelian varieties, I defined the theta function. I defined for you a theta function completely differently here for Jacobians. And the claim, which I never wrote on the blackboard, is it's actually the same thing, which by no means is clear, right? You need to say something. This is somehow miraculous. That this is the whole point of this is that I'm relating two different worlds. This is very arithmetic, right? Abelian varieties are sort of, there are modular forms, there is some arithmetic, there is very little geometry. It's very hard to introduce some interesting geometry on abelian varieties. They're too flat. The curves are much more geometric. There is lots of interesting geometry on curves. And this story relates the two successfully. And this is a geometric description of the theta function for Jacobians. The theta function, if you view this as this exponential sum, it has a very different nature, but this tells you some geometric properties. Thank you. Any more questions? I have defined a principal polarization for every matrix tau on the Ziegel upper half space. I could have equally defined a non-principal polarization for every matrix tau in the Ziegler upper half space. So if there is a thing called modular space of non-principally polarized abelian varieties for a given type of polarization. If I think about its universal cover, it's also the Ziegler upper half space, but that be taken a quotient not by sp2gz, but by another arithmetic subgroup. So I have made some choice, which I concealed. But what I have defined defines for any point in the Ziegler upper half space, there is a canonical way to associate to this tau in the Ziegler upper half space a principal polarization. Non-principally polarized abelian varieties will never be touched in these talks. They will never appear, which is why half of the time I probably just say abelian varieties and I mean principally polarized. More questions? Okay, let me continue for another blackboard with the interlude on the Schottky problem. Okay. So, as I said, this is a complete solution of the Schottky problem in genus 4. I know precisely what the image of the moduli of curves of genus 4 is within the modular space of abelian varieties. There is no such explicit solution, some such explicit characterization of the Jacobian locus within the modular space of abelian varieties for any G at least 5. Okay, this is. I mean, we haven't made progress, you might argue, in 150 years now, 140 years, right? That's not quite true. But nothing like that is known. In genus 5, we don't know. Some things are known. Where I'm going is a solution of the Schottky problem. It's a complete solution. It's less explicit in some ways, more geometric in some other ways. If you look at this equation, it's very beautiful, I think, combinatorially, whatever combinatorics means here. But if you ask me what the geometric meaning is, I'd be stuck, right? I mean, I do know, but not in a direct way. This is some formula. So some things are known. So maybe I should justify why I have been invited here. So I'll state a couple of results, which I'm not going to talk about, but where I have been involved. Theorem. This is joint work with Riccardo Salvatimani. It says the following. If I take this wonderful equation here, and I just write it in genus 5, it is not satisfied. On the Jacobian locus of curves of genus 5. That is a thing that's very easy to generalize. What I've written here was, some sum. I can write the same sum in genus 5. I should replace 2 to the 4 by 2 to the 5 for some obvious reason. And then there was a conjecture of either Belavin and Knizhnik or Docker and Fong, which was to say that the cosmological constant for E8 cross E8 and O16 superstring theories are the same. And no. Okay? So this doesn't work. So you cannot just generalize this equation and write something like that. However, there is something you can do, and this is joint work with Herschel Farkas and Riccardo Salvatimani. This is all recent. I mean, I was not alive when Schottky did his work, so this is much more recent than that. There is an explicit set of equations in theta constants we shall call F1, Fn, where n is the codimension of the Jacobian locus. Such that the Jacobian locus, its closure really, is an irreducible component of the locus where all of these are 0 inside the modular of abelian varieties for any genus. Okay? This is a so-called weak solution to the Schottky problem. Weak means that you don't characterize a locus, you characterize a Jacobian locus up to extra components. There is a long story of this. The first weak solution was known to Andreotti and Maya. This is also called Andreotti-Maya locus. There is a whole theory of that. We're not going that way. These equations are explicit, but they're not explicit enough that I'll just write them down on the blackboard from memory. And if I were, they would take up the entire blackboard. There are some nice combinatorics. We're very happy with them. You can check them. It's not so bad, but that's about it, right? They're definitely not enough to characterize a locus. They don't give a solution. So there are definitely other components. Absolutely, yeah. The point is that there is an explicit set. Yeah. Of course, there is always some defining equations, but that's the same, right? I mean, I'm trying to define a subvariety. So of course, there are some equations. When I said there are some equations that define the Jacobian locus, I've conveyed no information, right? So the point. No, I mean, there is no unique procedure. We write something which is a natural choice, but in principle, of course, the ideal of relations is much bigger than generated by this, and there is no reason to choose these generators. There is no parameter. I mean, there is combinatorics, but there is no continuous parameter. If that's what. There are combinatorial parameters. Correct. Yeah. I mean, there is some choice of some two torsion point as usual in this business. Maybe more than one two torsion point. Okay? So I could state the Schottky problem on some level cover, then this choice will disappear. But I'm not doing this. Okay? So, yes. Correct. Here I should say the word Gaga principle, right? So the way I defined the map from moduli of curves to the moduli of abelian varieties is some map which sort of I have to argue is analytic and algebraic, right? The way I define this, I never did this, right? Because I said what a Jacobian of one Riemann surface is. I have to say that if I vary curves, the family of Jacobian, if I have an algebraic family of curves, the family of Jacobians is also algebraic. I have never done this. I will never do this. The deformation theory of curves is something I'm completely ignoring for the purposes of this thing. So I really need to, there is a mystery here on the blackboard. It's the moduli of curves. I'm saying, oh, it's manifold. I mean, a stack or an orbifold, whatever. I never explained to you why. And that requires work, right? The fact that the moduli of abelian varieties is a stack is rather clear because I've written it as an explicit quotient. So clearly it has a complex structure as a stack, at least, right? Moduli of curves, you could do a nice semester-long course to prove that moduli space of curves is a good Deligne-Mumford stack. This is even for abelian varieties, I've clearly presented this as an analytic stack. I need to know it's an algebraic stack. Yeah, I can actually do this explicitly because the theta constants define an explicit embedding of the moduli space for abelian varieties with some finite cover thereof into a projective space. But there is a whole theory behind that. Yeah. I need many things. Yeah. There was another question. Was there another question? No? Okay. Okay. We still have some time. The interlude on the Schottky problem is over. So remember, the goal of this lectures is to present for you Krichever's solution of a Schottky problem in terms of flexes of Kuma varieties. And the goal of the next hour, which means not just today, but a good chunk of tomorrow, will be to finally state what the theorem is, right, geometrically. And we're not there yet, as you have noticed. So I haven't yet said what the Kuma variety is. I haven't yet said what the flex is. This will all come. Before we go, are there any questions? So again, we have the moduli space of abelian varieties, which is this arithmetically defined object. We have a moduli space of curves. For each curve, we have a Jacobian, which is an abelian variety, but has a beautiful geometric structure. And somehow when I say geometric structure of an abelian variety, I should really think about polarization, because somehow if I think of unpolarized abelian varieties, they're all the same. They're just complex stories. There is no I mean, it's not true, but somehow I really should think about the polarization. That's the interesting part. And the question is how to figure out if a given abelian variety is a Jacobian of some curve or a Jacobian of a given curve. That's where we're going. So now I'll ignore Schottky problem for a while, and I'll switch to more properties of Jacobians of curves for the next hour or so. But there was a question. So the question is whether these explicit equations that I'm getting here are going to get that equation in genus 4. So the answer is they're not going to give you that equation on the nose. This is also not what Schottky wrote. So if you look at Schottky's paper from 1880s, he doesn't write this equation. He writes something which I could write, which I do not remember on the spot, and which involves lots of combinatorial choices of theta characteristics of epsilon deltas, which turns out to be equivalent to this, which is far from obvious, which is the work of Igusa. Igusa was the one who discovered that the Schottky equation is equivalent to that. Our work generalizes not this, but the Schottky equation. So the combinatorics is already there. So if you take what we do in genus 4, you get precisely the Schottky equation in its original combinatorial form, not in that form. There is only a very technical answer to this question. So the question is the nature of the two descriptions different? So this is a nice, somehow a symmetric way. I made no choices here, right? Which is why I wrote this. Schottky was working on a level 2 curve of the moduli of curves related to Prym varieties. You need to choose some double curve. This means you choose some two torsion point in the abelian variety, so there is a combinatorial choice. Given that combinatorial choice, Schottky writes down an equation which a posteriori turns out to be independent of the combinatorial choice, but that's not at all clear. We are also making some a posteriori choice of a two torsion point, more than one maybe. It has to be equivalent, but the equation that Schottky writes is not does not define a divisor without a level structure. So it only defines a divisor on the level structure on a finite curve of the moduli of curves, then you push it down, then you get this. But this requires proof. More questions? Okay. So I want to continue with discussing theta functions on Jacobians. Okay. So remember we have the theta. This is a divisor in peak g minus 1, right? And theta, as was written and erased, is just a set of all things of this form, right? Where pi are points in the curve. That was my description of the theta divisor on the Jacobian. Okay. Now I want to use this. So somehow I didn't write this nicely. So this is just peak g minus 1 of the curve. Okay. So now I want to try to think of theta, which of course sits in the Jacobian, as a function of the curve itself. So let me tell you first that this requires thinking about the curve as sitting inside the Jacobian. So there is a double Jacobi map that takes a curve C and embeds it in its Jacobian, but sadly it doesn't quite go to peak g minus 1, it goes to peak 1 always. Which of course you can then identify with peak g minus 1, peak naught, but that's not canonical. So what it does is you take a point P and you send it to the point P. Here, this is a point on the curve. Here, this is a divisor on the curve. It's 1 times P. It's a linear combination containing just one point P with coefficient 1. Maybe I should write 1 times P, if that helps, right? It's a divisor. I'm thinking of the point as a divisor on the curve. Okay, so somehow I've embedded the curve in the Jacobian. In peak 1, it's canonically embedded. So wait. You should. This won't suffice. This won't fully suffice. So if you do this, pretend that this difference between peak 1 and peak g minus 1 was not noticeable, which of course we can't. Then I have theta function, where theta is a divisor on peak g minus 1, but the divisor is the same as a function. So I have a function on the Jacobian, which I can then restrict to the curve. I mean, the degrees of the peaks don't quite match, but never mind. So I have a function on the Jacobian, which I'm going to restrict to a curve via the abelian Jacobian map. So I'll get a function on the curve. So I'd like to know what function on the curve I'm going to get, right? This is the question I'd like to answer. So to make sense of this question, I somehow have to make sure that my degrees are correct. Because I know what the theta function is here, I somehow need to move it to here, right? So I need to take a variable point here in peak 1 and somehow stick it into g minus 1, right? So for that, I need to choose a degree, depending on how I do it, g minus 2, but I actually want to change some sign, so I'll choose a degree g divisor, right? So theta, remember, is a divisor, but it's also the zero locus of a function, right? Theta of tau z is 0, right? So when I write the small theta, I mean the theta function. I'm really thinking of this as a function. So I can think of the following function. Fix P1 through Pg in C and consider theta, and let's say a tau is a Jacobian of C. So the tau is the period matrix of C. Which I have defined last time analytically. And I consider this plus P2 plus dot 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 plus Pg minus Z, say, maybe minus X, as a function of X on the curve.
In other words, you are using a variable c into peak minus 1.
Correct. So what I've really done here is, for convenience, I've put a minus here and chose a minus, right? Because a peak A can always be mapped to peak minus A by changing the sign. That's what I did here. This is for convenience. Okay? And I was going to tell you an exercise about, there will be an exercise precise. I was planning to, Pasha is too fast, but I was planning to give you an exercise in a minute, okay? So this is a function of a point on the curve, right? This now makes sense because this is a divisor of degree g. I subtracted a point, so it became a divisor of degree g minus 1. So this gadget here is a point of peak g minus 1, right? And this is a function. So what is this zero locus? So observation, this is 0 if x is equal to pi for any I from 1 to g, right? Because if x is equal to some pi, I cancel this point, right? Because say if I look at theta tau, say p1 plus pg minus 1, this is 0, right? Because this is to say that the point p1 plus pg minus 1 lies on the theta divisor, right? And the theta divisor is precisely the locus of sums of g minus 1 points. So if I cancel one of these g points, then I get precisely 0. So this means I know g zeros of this function on the curve, right? Okay. Claim, fact. I'd love to assign this as an exercise, but I don't think it's doable unless you have some further machinery. The divisor of this function is p1 plus pg. This is to say that these are all x. Sorry. So this is to say that these are all the zeros. So all the zeros of the theta function are just these points. So what you need to to prove this fact is you need to compute the degree of this function, right? Which you can do if you know something about the intersection number with theta divisor. So, but we. This is a section of some bundle. So the divisor I defined for functions. It's also defined for sections of arbitrary bundles, line bundles. So this function, multi-valued holomorphic function on the curve, has a divisor given by just g points. And there was going to be an easy exercise here. The exercise is that theta is an even function. This is very easy. And the second question is, what is the theta divisor in genus 1? Very explicitly. And then somehow, can you see modularity of theta tau z with respect to tau for genus equal to 1? That has many stars, okay? So this is sort of to allay your fears about changing signs, because I'll be playing this trick again and again. I'll be very sloppy at some point with the signs of arguments of theta functions because it's even, and when I'm not worried about degrees, I won't worry. Okay? Okay. Now, the last thing I want to say today is that any meromorphic function f from C to P1, non-constant, no, I mean constant is of course fine, but I don't want to do this, can be expressed in terms of theta functions. Let me try to explain what this is. So I have a function f. Its divisor is going to be equal to some, to the sum of mi, pi, where mi, I, and z, right? I'm writing together the zeros and the poles of this function with multiplicities. So then I can just write down this function f in terms of theta functions, up to a constant factor. No. So claim, more precisely, is f is a product. So let's say this was I from 1 to capital N, I from 1 to N. Oh, I made a bad mistake. I'm sorry. Could we rename this guy as not pi, but xi? I'm sorry. Okay? And I'm just going to write here theta p1 plus dot 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 plus pj minus xi to the power mi for any chosen sufficiently general p1 pg in the curve C. Sufficiently general means they should be all different, they should be generic, they should be different from all the axes. That's a formula. This is just an explicit formula. Proof. if I take one of these terms, the divisor of such a term is just a locus. Sorry, no. Sorry. These are different functions. It's not always the same function. Otherwise, it would be a rather boring statement. So I've chosen g minus 1 points completely arbitrarily. Completely arbitrarily here, I really want them to be such that h naught of the corresponding bundle is 1 and not higher. So this is a generic point in the theta divisor, really. And then I've added one of my points xi, and this is my function of x, right? So the divisor of this thing, what is this? Well, this, of course, mi, because it's an mi's power, times wherever this guy vanishes. So this guy vanishes for x equal to this or that. So it's just p1 plus dot 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 plus pg minus 1 plus xi, right? But then this is a divisor of a function. So notice, since the degree of f over 0 and infinity is the same, the sum of mi is just 0, right? That's what I said before, that the divisor of any function has degree 0, right? So now if I take the sum of divisors, which are mi times p1 plus dot 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 plus pg minus 1 plus mi xi, this will cancel because this is just the sum of mi's plus the sum of mi xi, right? So this shows that this product will have the same divisor as this function. But then this means if I take one side, divide by the other, there are not going to be any zeros or poles. But a function on a Riemann surface without any zeros or poles is called a constant. So this means there is a constant here, okay, which I cannot determine, and that's free, right? So that's why I'll stop today, but I want to make some remarks. So this tells you how to recover all functions on Riemann surfaces from theta functions. This is a very weird formula if you pause to think about it, because I've just chosen a random point, p1 plus pg minus 1. It's a random point in the theta divisor, a general one maybe. But there are many choices here. And I wrote this expression, which manifestly seems to depend on these choices. But in reality, as it shows, it's independent of these choices. This will become even more mysterious after the first 20 minutes tomorrow, when something will look clearly wrong on the blackboard. But notice that somehow it all works out correctly, right? I mean, this ambiguity just cancels. And as an exercise not to be discussed, but for your own benefit, try to look at this and try to see how this relates to Abel's theorem. So there is an Abel's theorem for a curve which says that if we take the divisor, so we have the Abel-Jacobi map, maybe I should call it AJ, and of course this extends to a map of divisors. So the statement is that the Abel-Jacobi map of the divisor of f is 0, right? That's 1/2 of Abel's theorem. The answer is the full statement is if and only if. So this, of course, is related to this and can be deduced from here if you wish and so on. Okay, but I'm not going to discuss that. Okay. I can think about it this way. I can rather normalize things in a different way. So I will ignore this constant. Yes. The constant does depend on P1, Pg minus. The constant will depend on P1, Pg minus 1. Yes. Yes. But that's not how I will want to think about such things. That's it for today. Thank you.
There were some questions during the lecture, but are there any other questions? Let me check if there are any questions online. Okay. everything seems to be very, very clear. So thank you very much again, and we have a coffee break.
Thank you.